Do we respect the 5-minute rule here? 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 Good to start, Alex? Yeah, okay, cool. Okay, welcome everybody to this lecture. Thanks very much for coming. Yeah, as you've noticed, Russ is not here today. He's busy traveling, hanging out with some cool people in California. So he's asked me to give this lecture on direct policy search. Yeah, let's get into it. Okay, so first of all, why are we going to talk about this today? May as well sit down, comfortable. Direct policy search, I think, has received a real resurgence of interest in recent years. There's been some impressive success stories, certainly very high profile. You're probably familiar with OpenAI's shadow hand collaboration, in which they solved the Rubik's Cube. Also, OpenAI was playing this computer game, Dodo. I don't know much about it, but it looked very impressive from a layperson. And there's also been examples of applications of policy search, this technique, which we'll talk about a lot today, to problems in solving combinatorial optimization, optimizing graph neural networks. So it's received a lot of attention recently. It's also a relatively old idea. People have been doing direct policy search, especially in robotics, for at least a decade, maybe more. It has kind of roots going back to adaptive control from the 70s and the 80s, probably earlier as well. And some people, some big names in reinforcement learning would also even go so far as to say that reinforcement learning is direct adaptive control in some sense. So this is a bit of a, just a motivation that this is a relevant topic, that it's a little bit hot in research right now and certainly useful in practice. Okay, so what we'll be talking about today, we're going to be going through, first of all, the what and the why of direct policy search. Then we're going to talk a little bit about what I'll call the optimization landscape. When you're trying to solve this problem, it's an optimization problem. What does that optimization problem look like? We'll introduce some notions here that will be kind of qualitative and intuitive in the first part of the talk. And then in the second half of the talk, we're going to make them a little bit more quantitative. I will explain these terms as we go along. So this is a general plan. The main disclaimer I will give is that Russ asked me mostly to talk about the theory of direct policy search. So there's not going to be so many cool practical implementations on real robots or computer games today, but yeah, I think the theory nonetheless is valuable. Yeah, so let's get started. So far in this course, the lecture was originally called Policy Search, but I guess you've been doing policy search the whole time. So a typical problem in this course, I suppose, is that you're given some system. It's very abstract, so let's just think of this cart pole to make it more concrete and precise. And the system takes in an action U. This could be, I suppose, the force that you apply to the cart here. It outputs some observation, Y, or if you're lucky, you get the full state. In this case, the state of the cart pole would be the horizontal position, the angle of the pendulum, theta there, and their derivatives. Hopefully this is kind of familiar to you if you've seen Russ go through something like this before. Then we have a cost function, which is just a way of quantifying what kind of task we're trying to accomplish. In this case, maybe we have a quadratic cost that penalizes deviations from the upright equilibrium point if we're trying to balance the cart pole in that vertical equilibrium. And then the goal is to search for a policy. So this is something that takes in our observation or our state and outputs our action U. And for this simple problem, maybe you've seen some linear static state feedback policies. So the policy here is just a matrix K that multiplies by the state X. Okay, so in this class so far, I would understand you probably have somewhat of an indirect approach to solving this problem. So the first step, you would obtain some kind of model of the system. Maybe it comes from physics and first principles, or maybe you have to learn it from data. I think Russ was going to talk about system identification. Maybe that lecture got cut, but maybe you can do some modeling from data. And then in the second step, you use this model to solve some equation or solve some optimization problem. So you've probably seen Bellman's equation or the Hamilton-Jacobi-Bellman equation. And you probably also know that for simple problems with linear dynamics and quadratic costs, this reduces to something like the Riccardi equation. So your goal would just be to solve this equation for this matrix P in red. So hopefully this is kind of familiar, drawing connection to what you've seen so far in the course. And then the third step, which is why you might call it indirect policy search, is that once you've solved step 2, you recover the policy that you care about, K, indirectly. In this case, it's a function of the thing that you solve for, P, the solution to the Riccardi equation. Okay, so what are we going to do today? We're going to do direct policy search. So we can consider essentially the same problem setup, still have dynamics, still have a cost function. We have the same class of policies, but instead of worrying about the model, we're going to jump directly to the policy class. In this case, it's going to be this simple linear feedback law. So we'll have our policy parameters throughout the lecture. These will be theta. Here it's specifically this matrix K. And then we're going to compute or reason about the loss of this policy, what I call the loss of the policy. And this is essentially just if you pick a policy theta and you put it into the feedback loop here and you run the system, you will get some costs coming out of the system. And what happens if you just add them all up or integrate in continuous time for whatever time horizon you're interested in, capital T. Maybe it's infinity, maybe it's a short time. But this is basically just what cumulative cost do you get from the policy. We call that the loss of the policy. You can visualize it here as a function of the policy parameters, L of theta. And then in direct policy search, we search directly in the space of policy parameters. So we just try and minimize this loss function L with respect to the policy parameters theta. And we usually do so with some kind of fairly simple local search method, such as gradient descent. So you have the gradient, hopefully, of the loss function at some point, and you take a little step eta downhill, as it were, hopefully converging to some good solution, some good policy. So that's kind of the what of policy search. It's very simple in that sense. So let's just make clear that the differences between this and what you've seen so far. So in direct policy search, that's indirect, you recover the policy indirectly from some other quantity. So remember in LQR, you might solve the Riccardi equation for this cost to go function, and then you can back out, as it were, indirectly the policy K. In direct policy search, it's so named because you just search directly in the space of policy parameters. In the indirect policy search, you almost always have some kind of model of the system. It's usually important to set up the solution to the optimization problem, like the Riccardi equation or something like that. Without a model, it's very hard to do anything. However, in direct policy search, there's really no need for a model. It could be model-free, or you could use a model. The only thing you really need is to be able to compute the loss function and maybe its gradient so that you can optimize it. Direct model-free or direct policy search is usually very popular if you want to work in a model-free setting. And you'll see that a lot of the motivation for this direct policy search comes in model-free applications. So are there any questions? Yeah, if there are any questions at any time, don't hesitate to ask. So this is the what. Yeah, please.
When we say model-based, model-free, what model are we referring to? I assume it's not the system, like the dynamical model.
Yeah, I would say it is. So it's a good question.
Repeat the question.
Oh, okay, yep, sure. So the question is, when we say model-based or model-free, what kind of model are we referring to? What are we modeling? Is it the system? And typically, yeah, I would say it is the system. It becomes a little bit ambiguous. If you have a simulator, for instance, would you call that a model or not? On one hand, you clearly do. It's distinct from the real thing. It's an object that lives in the computer. It's abstract. However, a simulator may not be particularly useful for synthesizing a controller. So as an example, if you have a real kind of cart pole with all kinds of nonlinearities and funky things that are difficult to model linearly, you might have a very accurate simulator, but you can't do LQR on that nonlinear model. So you might end up doing a model-free method with your simulator as opposed to a kind of model-based method with your simple linear model. So I don't know if that answers the question exactly, but yeah, the model of the system is what we have in mind, including the cost function. That's a great question. OK, so before we kind of dive into studying this direct policy search, let's just look at some motivation for why you might actually want to do this as opposed to the indirect one. So again, a lot of the motivation comes from the model-free applications. And I think one compelling reason why you might do a direct policy search is that when you do so, you're optimizing for the performance of your policy directly on the true system rather than on an approximate model. So in a model-based method, you have to come up with a model first. That model is almost always wrong. There's always some error between the model and the true system. And when you run direct policy search directly on the true system, you obviously have no such gap. So you're really optimizing for what you care about, the performance on the true system. Another reason why you might consider doing direct policy search, again, comes from kind of a model-free motivation, is that sometimes good policies can be simpler than good predictive models. So here's an example from some work from Russ's lab from a few years back, and we see a very simple policy for picking up a plate here. It's quite simple, slide it along, tilt the plate up, and grip it. Full disclosure, this was not trained with direct policy search. This was imitation learning, but the point still stands that it's a simple policy. And now consider the same environment, but with all this clutter. You've got napkins and lemons and stuff. Even though that environment might be very difficult to model and questionable what is even important to model, should you model the hot sauce in the background or not, the same simple policy works. So this is an example where a good policy is probably easier to find than a good predictive model of the system, including all that clutter. And the final reason why they're attractive is that they're just very simple to implement these direct policy search methods and very broadly applicable. So there's no need to develop a complex model, like with that plate pushing example from before. Do I model the lemon or not? Also, there's no need to kind of try and solve the Bellman equation if it's nonlinear. Maybe that's difficult. You essentially end up just running gradient descent. So it's very easy to apply and has worked well in that shadow hand Rubik's Cube example, as well as combinatorial optimization. So these are some of the reasons why you might consider doing it. OK, so that's the end of the first part of the motivation. Again, if there's any questions at all about the setup or why we do this, jump in at any time. So now let's look more. Yeah.
So what are the cons of using direct policy search in comparison to the other methods that we've been studying in class?
Yeah, that's a fantastic question. Seeing as how you asked the question, I would just jump. I didn't want to bum everybody out by going through the downsides straight away, but seeing as how you asked, let's just go there right now. Yeah, at the end, we're going to kind of do a critical appraisal of why you should do this. So fortunately, it's very fresh in our mind. We had this idea that there's no model error when you search for policy directly for the true system, so that's good. But the downside of that is that you don't have any guarantees for any other system as well. So if maybe you have a different system that you'd like to apply it to, now you have no idea how that policy will behave. Whereas if you used a model-based method and maybe did some robust control, you could have some guarantees for a whole set of models. So then you could say something about the behavior for a different system. The second advantage that sometimes good policies can be simpler than predictive models, like with this cluttered example here with the plate pickup thing. The converse is also true in that sometimes it's easier to come up with a good predictive model than it is a policy. So if you have a drone or something like this, we're pretty good at modeling how drones fly, and we certainly know how to model how a drone reacts with a wall. It crashes, it's not good. So it's much easier, I think, to model the dynamics of the drone and set up a model-based path planning problem than it is to somehow search in the space of model-free policies directly for collision avoidance. And then the final thing, which is going to jump the shark a little bit because we haven't seen the rest of the lecture, is that this claim that it's simple to implement and broadly applicable is true, but it may not always work. It may not always be very effective. So I'll probably take the rest of the lecture to spell this one out. But yeah, that's a great question. Yeah.
How much of the first point just comes down to like state estimation? Like if you could do perfect simulation on the real world, bring it into physics world, then like the model-based methods will always generalize. Because in practice it's very hard to get like contact forces, all these things. How much of it is that versus is there something else?
No, I think that's a great question. I think sometimes that's. Oh yeah, sorry. How much of the motivation for the first plus of model-free policy search is due to the fact that state estimation is difficult, and if we had full state estimation, especially with contact forces, maybe we could just use model-based methods, and they should generalize very well because probably they're based on physics models, and physics should generalize well. I think that's largely true. It's certainly the case that you may want to do direct policy search to bypass these questions of state representation. Like with the plate, for instance, that's one of the main advantages. You don't have to consider the full state of the system with the state of the lemon and the state of the napkin. You roughly know what the right policy is. But sometimes, even if you do have full state information, you might have nonlinear dynamics that are still complicated to reason about. It might still be hard to solve the Bellman equation, and a good policy might be fairly simple. Maybe it won't be optimal, but you're better off kind of searching in that space of simple, effective policies. So yeah, I think you're right to a large extent. Yeah, okay, great questions. Okay, so let's jump back to the lecture. Okay, and move on to the landscape. So far, we've had this idea that we have a loss function. It's a function of the policy parameters and is roughly speaking telling us how good a job are these policy parameters doing at solving our task. And naturally, we want to optimize this loss function. But this is a cartoon, clearly. It's a very nice function. It's nice and convex. What do loss functions look like on real examples, on real systems? Okay, so here's a very simple example. Don't worry too much about the specific numbers. I kind of extremely contrived. I plucked them out to make the plots look nice and make the point. But the key point is that the dynamics are linear here. So hopefully you've kind of seen the linear dynamics before, fairly simple linear dynamics. The cost is quadratic. So again, nothing too funky going on, just a very simple quadratic cost on the state and on the action U. And the only maybe slightly tricky thing that will raise an alarm bell is that we have this partial observation. So instead of being able to have full access to the state x, this goes to the previous question a little bit, we only get what we would call partial observation. That is, the observation y is a linear function of the state. So we get to see, in the first output, we get to see x1 plus x2 plus 3 times x3. So at no point do we get to see x2 just by itself. So hence the name kind of partial observation. And then as a result, our feedback is going to be this simple linear feedback law, but instead of operating directly on the state, we have to operate on this partial observation. So the feedback policy, it has two gains, K1 and K2, for the two outputs. So this is the example. It looks fairly innocuous, linear dynamics, quadratic costs. But if you plot the loss function, now hopefully this is fairly clear, but I should have, we can bring up the loss function in MATLAB just to get a bit of a better look at it. So if we look at the loss function, so just to be very clear, this axis is K1. Remember the policy has two parameters, K1 and K2, and the height of the function is the cost. So we're looking for the lowest point of this function when we optimize it. It looks pretty nice, like it's this nice kind of boat or bowl kind of shaped function. We would expect gradient descent to converge down somewhere near this optimum here, except if we look carefully, it's not actually the optimum. There's this annoying part of the function over here that is clearly a lot lower than the minimum in this part of the function. So we can see that even clearer if we go back to the slides here, and I just plot it in one dimension. So I just take a slice along K2 is equal to 0. You can, and I stretch out the axis a little bit with log scaling. You can see that there's clearly this this is the global optimum here, and this is clearly a local minimum. So if we were to start gradient descent anywhere here, we would get stuck. We wouldn't find the best policy. And this is typical of loss functions in general, this non-convexity, that is. So let's see. Yeah, first of all, any questions about this? Yeah, jump in if there are. So the first question is this kind of non-convexity surprising? Is it something that we should expect? So let's just look at a very simple example. I'm going to switch to discrete time just for this example. It just makes it simpler. But as you know, discrete time and continuous time, not so different when the time step gets very small. So we have these discrete time dynamics. Again, they're just linear dynamics. We have the same, this time, state feedback law. So the action is a linear function of the state. And what we're really interested in is our policy parameters. So I've highlighted them in blue. It's this matrix K. So the first thing we can do is just simplify how the state is going to evolve. So instead of having this U, we just plug in K of X. So we've just plugged in our control law into the dynamics, and then we just factor out the state, X of T. So this is just describing how the state transfers from one time step to another. And then we can look at how this is going to evolve. So after one time step, the state at time 1 is clearly just one step of the dynamics, given the state at time 0. Quite simple. After 2 time steps, this is the law from 1 to 2, and then we just plug in what the first state was, which is right here, and so we get this term showing up. And we can see that when we multiply these things together, we're getting this quadratic showing up. So already a little bit of non-linearity is showing up in our response, our system response. And if we were to continue this after n time steps, you can probably see how the pattern emerges. We get that the key point is, I'll emphasize that the response of the system as a function of the policy parameters is nonlinear. In fact, it's a polynomial. So already we should expect that just the system response is going to be a very nonlinear function of our policy parameters. If we put that into a loss function as well, all kinds of crazy nonlinearities and non-convexities could show up. So it's not too surprising that these loss functions are non-convex in the policy parameters. Okay, so you might at this point be thinking that we're kind of doomed. We've got these non-convex functions. We're going to try and optimize them with gradient descent. We're just going to get stuck. Policy search is probably never going to work. So that's probably because we have this kind of typical picture of convexity in mind. On the left-hand side, we have a nice convex function. It's kind of like a parabola or a bowl. If you start gradient descent anywhere, it's probably going to converge to the global minimum. That's nice. And on the right-hand side, we have like a classic example of a non-convex function. It has this quite distinct bad local minimum here, and if we were to start gradient descent here, maybe, then we would get trapped. So that's what we have in mind. The good news is that not all non-convexity is bad. Sometimes you can have what you might call benign non-convexity, which means that even though the function is non-convex, so even though the function is not always above its tangent, if you look at it, it doesn't look so bad. If you were to start gradient descent anywhere, there's no local minima for it to get stuck in, and gradient descent will probably converge just fine for this function. So the key question that we need to answer when we're talking about direct policy search is what kind of non-convexity are we dealing with? The pathological kind, where we'll get stuck, or this benign kind? Okay, so yeah, any questions on that so far?
Why don't we see this problem with non-convexity with LQR?
Okay, yep, that's a great question. We're going to explore that a lot today, and a key kind of result, sorry, I always forget to repeat the question. Why don't we see this kind of problem with non-convexity in LQR? A big theme of what we'll see today is that LQR fortunately falls into this category of a benignly non-convex problem. Yep, that's a great question. Okay, so if we go back, and in fact, we'll see it right now, in fact. So if we go back to this simple example where we saw the kind of pathological non-convexity showing up, recall that we had this kind of partial observation model. So we didn't get to see the full state. Our feedback policy was a function of the output. We didn't get to see all the states. So if we replace it, like in the question just now, we replace it with a full state feedback model. So now our action U is a function of the full state X. Now we have 4 scalar parameters in our policy, 1 for each state, of course. So now we're kind of back into the LQR setting. I probably should have said that we're looking at the infinite horizon cost here. So before I had this integral, this is integrating for all time, for t is equal to infinity. So now if we look at this LQR example, and we plot the loss function, I think it's probably clear, but we can do the same thing and look at it in MATLAB. And so this is what it looks like for state feedback. We can see now, unfortunately, it has 4 parameters, so we can't really plot all the function as a function of all 4 parameters very easily. But I take a slice of just 2 of the parameters to get the feel for it, and we can see that it's not a terribly nasty-looking function. Certainly, there's none of those nasty disconnected parts where the real global minimum was, and then the fake local minimum was somewhere over here. It's kind of nice. So if we go back and take a look. If we look down from the top of the function so that we can see the sub-level sets, it is clear that there is some non-convexity in the function. The level sets of the function are not convex. If you take 2 points in one level set and draw a line between them, it doesn't stay within the level set. But it's a very benign kind of non-convexity. You can imagine, hopefully, that if you start gradient descent anywhere, it's going to kind of trickle down to the global optimum anyway. So this comes back to the question from before. This is LQR, and it has this nice benign non-convexity property. Okay, so yeah, this is the kind of picture we have in mind at the moment. Pathological non-convexity with bad local minima that we could get stuck in. Benign non-convexity, where we can expect gradient descent to work. And the question remains, for any given problem that you kind of throw at me, how do I know what kind of non-convexity I'm going to be dealing with? And the approach that we're going to take in this lecture is to answer this question. So it's an analysis question. Via this idea of convex reformulations. So that probably means nothing at the moment, but that's what we're going to talk about next. So this is the next part of the lecture, how we can answer this question with convex reformulations. Okay, so the first question, of course, is what do I mean by a convex reformulation? So at this point, we're going to step back and make it a little bit more general. I'm going to be talking about this function f. But if you want to think of f as the loss function L, that's totally fine throughout. But you can also think of f as a generic non-convex function, if you like. Okay, so here's our, in this case, non-convex function, f of theta, down here. And we say that this function has a convex reformulation if there exists a change of variables. So the original variable was theta. We have these new variables, nu. Hopefully that's more helpful than it is confusing. And this mapping phi between them. And phi has to satisfy 3 important properties. So the first, which is where the name comes from, is that phi has to be such that if you were to make this change of variables, that is, you take f of theta and you plug in, instead of theta, you plug in phi of nu, you get a new function, h of nu, defined as follows. And that function should be convex in nu. So here's the new function, h of nu, over here. It should be convex, hence the name convex reformulation. The second property is that this change of variables phi, it should be surjective or onto, meaning that for all of the theta, if you pick any theta over here in this non-convex space, you can always find over in the convex space some value nu such that nu maps back to theta under this mapping phi. So the fact that it has to work for any theta that you come up with, that's why it's surjective or onto. And the final property is that this mapping phi should be differentiable. And roughly speaking, the reason is just so that this new function h remains smooth. We don't want to introduce any nasty non-smoothness with this change of variables. So that's what I mean by a convex reformulation. Are there any questions about the concept? Okay, so here's a concrete example of one. Again, this is not for a control problem. This is just for a generic function. So here I've picked arctan. So you're probably familiar with, I've picked arctan squared rather. You're probably familiar with arctan. It kind of plateaus out a little bit. And I've just squared it so that it curves up again here on the other side. And you can imagine that what we really need to do to make this thing convex is to undo the arctan function. So for our change of variables, this mapping between the new variable nu and the original variable theta, we can just pick tan. So then when we plug this thing in, arctan kind of undoes the tan, so to speak, as its inverse. And what we're left with is just the square of the new variable. So this nice quadratic function here is our h of nu, nice and convex. So that's the kind of thing that I have in mind, just to make it a bit more concrete. Okay, so this is the convex reformulation. Why are they useful? And let's remember, the question we're trying to answer is, how can we tell whether the kind of non-convexity we have is benign, like this picture here, or pathological with some kind of local minimum? Okay, so let's see how this concept helps us with that question. The nice result is essentially that if you have a convex reformulation, all of the stationary points of your function are globally optimal, global minima. So precisely what I mean is that if this function admits a global minimum, so f star is the minimum of this function with respect to theta, it would be the value down here, then as long as we have a convex reformulation, whenever the gradient goes to 0, that is, whenever we have a stationary point, or sometimes called a critical point, whenever the gradient goes to 0, that implies that we must be at the global minimum. And you can kind of see that here in the cartoon. So this statement is, or this proof rather, is so simple that we can prove it right now. We can do so by contradiction. So let's suppose, contrary to the statement, that we actually do have a suboptimal stationary point. So I'm going to introduce one here. I just flattened out the function. So the gradient here is now 0. Remember, we're kind of proved by contradiction. So I've introduced a suboptimal stationary point. Clearly, this is not the same value as the optimal here. Right, OK. So here's our suboptimal stationary point. And now we're going to go back to this assumption that this mapping phi is surjective. So that means that for any theta, in particular this theta bar, which is our local minimum, we can, or rather our stationary point, I should say, we can always find over here in convex space some new bar that would map back to theta bar under the mapping phi. So it should take on the same function value as well. Recall that h of nu here is just the same as putting in the change of variables. So as you can see here, both points have the same function value, even though they live in different spaces. OK, now here's the only equation that we need in the proof. We would like to compute the gradient at this point. So we remember that we get this function from putting in the change of variables. And then we can just use the chain rule. So to get the gradient of the function h with respect to nu, first I need to take the gradient of f with respect to theta. And then I need to multiply that by the gradient, or rather the Jacobian of this mapping, the Jacobian of phi here. And I should be careful about where I evaluate these. I want to evaluate the gradient at nu bar. And likewise, I want to evaluate the gradient over here at theta bar. OK, so hopefully so far so good, just the chain rule. Now we have the observation that because the gradient over here is 0 by assumption, this was a stationary point, so the gradient here is 0, it must be from the chain rule that if we plug in 0, the gradient over here at nu bar in the convex space should also be 0. It's a kind of simple argument. But if we look at our picture, this looks like a contradiction. The gradient here is clearly not equal to 0. But maybe I just drew a bad cartoon and the gradient should be 0, but I messed it up. But that can't be the case because recall that h is a convex function. So the only place that the gradient is allowed to vanish at a convex function is down here at the minimum of that function. And clearly by construction, this point was not at the minimum. So this is a real contradiction. And we've really ruled out the fact that this cannot happen. We cannot have this suboptimal stationary point in our function, as long as we have this convex reformulation over here. OK, so let's, any questions on that? It's a lot to digest, but really the crux of it is just the chain rule. And if you have a convex reformulation, it's not possible for the gradient to vanish in one space without it vanishing in the other space. And because in that space it's convex, the gradient can only vanish at the global minimum. OK. OK, great. So that's I would just kind of be driving that home now. If we have the convex reformulation such that when we plug in this change of variables, our non-convex function becomes convex, then any stationary point of the original non-convex function has to be global optimum. OK, so there's a couple of questions that remain unanswered. The first and most natural question is probably, for which problems do these convex reformulations exist? That's very nice, but do they actually show up for anything other than arc10 squared? And the good news is that for quite a few problems, like LQR and like also Markov decision processes, maybe Russ has talked about kind of finite state action problems in the class. If not, these are very kind of popular model for decision making and reinforcement learning. So for these problems, convex reformulations do exist, but certainly not for all. Another question you might have is, what about approximate stationary points? So we know that the gradient can't completely vanish unless we're at the global minimum. But what if the gradient gets really, really small at a very bad point? I mean, that might still be problematic. Gradient descent might still slow down or even get stuck around there. So we need to maybe worry about that. And also, what if the mapping is not really defined for all possible inputs and outputs? It's kind of reasonable to expect that the loss function is only going to be defined for certain policies. Maybe some policies won't stabilize the system, so the loss function will blow up to infinity. Like, is the convex reformulation going to work when the function blows up to infinity? Doesn't seem like it. So we need to be a bit careful about where the mapping is actually defined. And there's probably other questions as well, and if you have them, please don't hesitate to ask. So for the rest of the lecture today, we're going to look at these answers to the first two questions. Studying these mappings and where they get well defined can get a little bit technical, and I think it kind of clouds a lot of the key insights, but I'm happy to talk about that offline, some of the more mathematical, like mechanics of this kind of analysis. I should also just try to flag where this argument comes from. As best as I can tell, it's kind of village wisdom. I heard it from somebody at a conference, but in 2018. I'm sure it's much older than that. I think it's something that is so obvious to some people who know about it that no one ever wrote it down as a paper. At least that's what my source tells me. It's starting to show up though in some papers. Not this very simple argument, but building upon it. So there's some relevant literature you can check out if you'd like to know more. Okay, so back to our outline. Any questions about the optimization? Yeah.
So the main point of the previous argument was that it's okay to just do local optimization of the original problem and you still get a global optimum? Or would you rather optimize the reformulated problem and then try to map it back?
Okay, yeah, great question. I remember to repeat it. So the question is, was my main point that you can optimize that original non-convex function and still find the optimum? Or should you consider, if you have this convex reformulation, maybe you want to somehow search in that convex space? That seems a lot nicer. It's a fantastic question. So I would say that if you have the model, a lot of these reformulations are model-based. You need to know the model to be able to reconstruct the convex function. So if you happen to have the model, I think it's probably better to search in the convex space. You can usually reformulate it as a kind of, we'll see later how for LQR you can reformulate that convex optimization problem as a semi-definite program. I think Russ has talked about semi-definite programming maybe a little bit. These are kind of nicer to solve than gradient descent. The value for this, I would say, is when you're in a model-free setting, especially, and you can't make that, you can't actually implement that convex reformulation, and you have to search in the original non-convex space. Then this just the existence of this reformulation tells you that search in the non-convex space will work. So yeah, fantastic question. Okay, so now we're going to try and make this a little bit more quantitative. So I'm just going to switch over to the iPad, and I hope that the resolution will be sufficient. Okay, is that working for people roughly? I'll try and write. If I'm writing too small, if it's not clear, please let me know. Okay. Okay, so yeah, let's try and make some of this a little bit more quantitative now. So we have this nice picture in mind of a function like this. It's what we've called benignly non-convex, and we have this theorem really that says that all stationary points of the function, here's the only stationary point down here, are globally optimal. We ruled out the possibility that maybe you could get some kind of stationary point showing up here. But let's try and make this a little bit more quantitative, especially taking into account that question, or what about if the gradient gets very small somewhere that is still highly suboptimal? So to make this quantitative, we have the following notion that I'm going to call, it's known as gradient dominance. So let me unpack it here. Here we have what we would call the suboptimality of a particular point theta. So let's draw it here. Maybe red is good. we'll pick a particular point here, theta, and we'll go up to the function value. So here's our f of theta here. And what we're interested in is the difference, or the error, or the gap, you might say, between that and the minimum of the function. So here is our suboptimality gap. Sometimes I'll call this minimum f star, just to, as an abbreviation. And what this condition says is that this suboptimality gap should be upper bounded by the norm of the gradient, in some sense the size of the gradient, with some kind of scaling factor. Don't worry too much about 1/2. This is just to make it more convenient for analysis later on. You kill a 2 that's showing up. You could put the mu on top as well. It's purely for convenience. The point is there's some kind of scaling factor, some constant that makes the gradient dominate or upper bound what I call the suboptimality gap here. Okay, so first of all, straight away we can see that if the gradient happens to go to 0 at a stationary point, then this whole right-hand side goes to 0, which implies that the suboptimality gap also must be 0, because it's upper bounded by 0. So straight away we recover this statement that all stationary points are globally optimal. So that's kind of nice. We've made it a little bit more quantitative. But again, the real point is that now we have some notion of when the gradient is small, when we're getting near an approximate stationary point, maybe the gradient gets very small up here somewhere in the function, how suboptimal can we possibly be? And this kind of condition, if the function satisfies it, this is something that the function must satisfy, and not all functions will, it gives us a way to kind of quantify that. A special case of this is called the Polyakaloyevich PL inequality, abbreviate for PL for obvious reasons. And this is just a slightly stronger version of the gradient dominance result. We have that the norm squared has to upper bound instead of just the norm. So it's like a strengthened form of gradient dominance. Okay, so let's see an example of this. So here's a function that I've plotted down here. It's theta squared plus 3 sine squared theta. So most of the function is coming from this theta squared term, and we're just getting a little bit of wiggle from the 3 sine squared. So this function satisfies this strengthened gradient dominance, this PL condition. In other words, the suboptimality gap is always upper bounded by the gradient, the norm of the gradient squared, with the particular coefficient of mu 0.175. Don't worry too much about this number, just what it happens to turn out to be for this function. So here we're plotting the original function as well as its gradient. You can see that, yeah, it crosses 0 where we'd expect, and it's obviously positive on this side, negative on this side. But when we square the norm of the gradient, here the gradient is just a scalar, so the square, the norm is just the absolute value. So if we square the gradient and we scale it up by the appropriate scaling factor, it's kind of truncated here, but you can see that in fact the gradient squared is upper bounding, and very tightly upper bounding the actual function. By the way, the suboptimality gap here is just the function, because the minimum value of the function is 0. So this is just a concrete example of a function that satisfies it. And you'll see it looks a lot like our cartoon picture of our benignly convex function that we've seen, benignly non-convex function that we've seen before. Okay, it's a concrete example. It's probably maybe useful at this point to point out some relationships to other notions of benign non-convexity that maybe you've come across. One is quasi-convexity. So just to recap, we say that a function f is quasi-convex. There are a couple of different definitions, but I think this is the most intuitive. If each of the sublevel sets of the function are convex sets. So specifically, let's look at the definition here. If we pick any alpha, so any particular alpha, let's pick like 6, draw a line at 6, and then we look for all of the theta for which the function is below that value of 6. So here it is here. We can draw. So these are all the thetas in that sublevel set. You see, it's a nice line. It's a nice convex set in one dimensions. There's no kind of break over here. You can imagine if the function dipped down, then we would end up with a sublevel set that included this component over here, and that would be non-convex. Okay, so this is a nice quasi-convex function, and as we've seen, it's also a gradient-dominated function. It's the one from the previous slide. Here's an example of our cartoon from earlier that we used in the proof. So this one, by construction, had a suboptimal stationary point here, so the gradient here was 0 by construction. And you can see that the level sets of the function are still convex. If you pick any point, even here, and you go down and you look at the level set, you can see it's still nice and convex. There's no dips or anything like that. But this one is clearly not gradient dominated. Why is it not gradient dominated? Because the gradient goes to 0, even though the function is not at its minimum point. So clearly the 0 does not upper bound a non-negative number. Okay, so this is just to make the point that there is some difference between quasi-convexity and gradient dominance. But you might be thinking that, especially if you look in one dimension, that anytime you have this gradient dominance, it's going to imply that you have quasi-convexity. And that's not the case if you look in 2 dimensions. So here I have another function here. This is the arctan squared. It's kind of like our arctan squared example from earlier, but now I've plotted it in 2D. And here's our LQR loss from earlier as well. And so now if we look at the sublevel sets of each of these functions here, we can see that this function here, the arctan squared one, has nice convex sublevel sets. Again, this is looking down. So this is definitely a quasi-convex function, but it's not a gradient-dominated function. Why is that? Because eventually this function is kind of fanning out like arctan, so the gradient's going to go to 0. So eventually, at some point, the gradient's going to be too small to possibly upper bound the suboptimality gap of the function. Conversely, if we look at the LQR cost function, we can see that it's definitely not convex. Again, a line between 2 points is not going to stay within the level set, so it's not quasi-convex, but it is gradient dominated, and we'll see that a bit later, hopefully if we have time. Okay, so that's just to maybe contextualize it and make the point that it is a kind of orthogonal notion to that of quasi-convexity. Are there any questions about any of this so far? Okay, so we had at the beginning this kind of qualitative notion of benign non-convexity, and we replaced it with this gradient dominance condition. Again, that the norm of the gradient should dominate or upper bound the suboptimality gap. And we also, from earlier, we had this nice kind of picture of convex reformulations. If you have this benignly non-convex function, or rather if you have this convex reformulation, you can kind of certify that your original non-convex function was benignly non-convex. Can we find a relationship between these two? Can we kind of make this picture a little bit more quantitative as well? So that's our goal next. I think we're doing okay for time. Okay, so specifically the result that we're going to prove now is that if you have a strongly convex reformulation, so far we only talked about convex reformulations, but we're going to extend that just a little bit to strongly convex. If the function f admits a strongly convex reformulation, then f is going to satisfy this PL inequality. And remember, the PL inequality is this gradient dominance condition with the strengthened requirement that you have this square up here. Okay, so let's see how this is going to work. So again, let's just go back and think of a convex reformulation. So we say that this function f here has a convex reformulation if we can plug in this change of variables, phi of nu, and we get back a convex function h. So this is here's the definition of convexity. Hopefully you're familiar with it, and we can draw a nice little picture. So let's say we have a convex function. Maybe it looks something like this. What it's saying is that, all right, h of nu. Is that big enough? Okay, let me know if I need to write bigger. So here's h of nu, and here is our tangent. So this is this function here, evaluated at, I should write it as nu prime, just to make it better. And this is evaluated at the point nu. And what this is saying is that the function should always remain above its tangent for any values that you pick, any tangent that you pick, as well as any function value that you pick. Okay, so that's convexity. Just to recap, we have this notion of strong convexity. If in addition we add this extra term here, now let's see. I think how do I want to define this? Probably like this, m over 2. So this is just some constant, m, just a scalar value. And we want to look at the norm of v, of nu, nu prime minus nu. So here's this quadratic function. So if h satisfies this inequality, we say that it's strongly convex, or m strongly convex. And maybe you've seen this kind of before, but the idea is that instead of the function just having to sit above its tangent, we kind of strengthen the requirement that not only does it sit above the tangent, it also sits above this quadratic function. So if we can kind of add in this quadratic function like this. Maybe it looks something like that. And this is clearly, this is now this whole function here. It's some kind of quadratic. It's like a local kind of quadratic approximation of the function. And the function has to sit above that. So it's a kind of strengthened notion of convexity. Okay, so that's what it means to have a strongly convex reformulation. This function that we get when we plug in the change of variables is strongly convex. Now let's see how we can recover this PL inequality from here. So the first thing that we're going to do is, maybe I should write the PL inequality somewhere, but it'll show up soon enough. The first thing we're going to do is minimize both sides of this inequality with respect to nu prime. So let's write that in now. Minimum, okay, maybe I need to write a little bit larger. Minimum with respect to nu prime, and min with respect to nu prime here. This is the whole thing I'm minimizing. I can do that, I can minimize both sides. It has to hold, this has to hold for all nu prime, so it certainly has to hold for the particular nu prime that is going to minimize it. Now, let's compute these minima. So the first thing we can look at is this left-hand side. And if we go back to our picture here, let's draw a line from here to here. We can see that the minimum down here, let's call it f star, the minimum of f is going to be the same as the minimum of h that we're looking at down here. That should hopefully be clear because it's really the same function, just with a change of variables. So if we want to minimize with respect to nu and get down here, it's the same function value if we were to minimize with respect to f. So we can replace this with, this is the same as the minimum with respect to theta of f of theta, which we can call f star. Now we're going to look at the right-hand side and do the minimization. It's getting a little bit messy, isn't it? But the first thing to notice is that this term, just the h of nu, that's not going to show up at all because we're just minimizing with respect to nu prime. So that's just a constant. So now we can look at this term here. And this is just a quadratic function. So we should be able to, in fact, it's a convex quadratic function as well. So this should be pretty straightforward to minimize. So we do the usual thing we do when we want to minimize a quadratic or a convex function. We take the gradient and set it to 0. So let's take the gradient of this function with respect to nu prime. So the first thing we get is just this h of nu showing up. That was coming from this term here. This part would be constant, so we only need to worry about this. By the way, I should probably say that thinking of this as like a row vector, the gradient, and thinking of these decision variables as column vectors, so that multiplication makes sense and wrong thing makes sense and gives you a scalar. Okay, so that's the first term. Now let's turn our attention to this one. This one we take down the 2, as it were, so we're left with the m. There's a plus there. And we should just have v prime minus v transpose. So again, thinking of this as a row vector, and this as a row vector too. So this is the gradient, and we want to set it to 0 if we're trying to minimize this quadratic. So we know that, maybe it's annoying to have these transposes flying around. So let's transpose both sides, get rid of the transpose there, put it over here. Now that would be like a column vector, and over here we've got our, what did I do? Yeah, good. We've got our column vector. Okay, makes sense, 2 column vectors. And so we can see that at optimality, this equation has to hold, the gradient has to be 0. So let's just write it like this for convenience. Nu prime minus nu has to satisfy minus, just going to take this guy over to the other side, minus the gradient transposed over m. That's the condition it has to satisfy for the gradient to be equal to 0. And now we're just going to plug it back into the function. So it's looking a little bit messy, but let's first look at this term here. So again, what I'm trying to find is the minimum with respect to nu prime. So if we plug it into this first term over here, sorry, wrong function again, plug it into here, we're just going to get the gradient of h times minus over m. And again, remember, we're thinking of this as a row vector, this as a column vector now because of the transpose, so this makes sense. It's just going to give us another scalar. And then over here, for this second term, when we plug it in, we're going to get plus m over 2. Then we're going to have this thing squared. Let's just take out this m straight away. So kind of 1 over m squared, so we don't have to worry about it too much. And then the norm of nu squared. That's just coming from, that's just coming from this thing times this thing is the norm. Okay. Any questions about this so far? We're just minimizing a quadratic here. So probably easier to do than it is to explain in some sense. Very simple. So now let's just kind of collect all these terms, and we get a minus, write it down, over m. Might be getting a little bit small, but this is this term here, just combining these two to get the norm squared. And then we add this m squared is going to obviously cancel out one of these m's up the top. So we're just going to get 1 over 2m down here. And again, the gradient squared. So when we add it all up, we should have a minus 1 over 2m. So it's minus 1 plus 1/2 essentially is minus 1/2. Got the m's on the bottom, and we've got the gradient up the top. Okay. So that was just minimizing. Not as nice as the other proof, right? But okay, so that was just minimizing the right-hand side of the equation. So let's do a little bit of rearranging and collecting some things. So maybe I can kind of sneak it in over here. So far, if I look at this term here, I had the f star, then I had it upper bounded here. I had my h of nu, which I didn't touch for the minimization because it was constant with respect to nu prime. So here's h of nu. And now I have this term that we just came up with after the minimization on the right-hand side. So that's should be minus 1 over 2m h squared. Okay, so hopefully it's not too much of a jump to see that we could, how would we like to do this? Let's leave this here. Let's take this, we subtract this from both sides, and let's add this to both sides, and kind of flip everything over, and you can see hopefully that we recover this equation here. So we've just done some rearranging of terms so far. And now it's starting to look a little bit more like the inequality that we're shooting for. We've got something that looks a little bit like the suboptimality gap on this side. It's upper bounded by something involving a gradient squared on the other side, so we're making some progress. The only thing that we have left to worry about is that we've still got these h of nu's floating around when we really want everything in terms of f. So let's get rid of those. the first thing that we can do is just realize that this here is nothing more than f of theta, as long as, of course, theta is related back to nu via the change of variables. So if we go back, it's the same kind of argument that we've had all along. For any point, we have this nice relationship between the two of them. Snap it on here. Pick any nu, and it's going to map back over to some theta. So that's just by definition. We can replace the h with the function f. And now this term here is relatively straightforward. We just need to go back to our old friend, the chain rule, and we can express this in terms of the gradient of f and the Jacobian of the change of variables again. So as a reminder, we had h of nu equal to f with the change of variables, v nu in there. So we can have that the gradient of h is nothing more than the gradient of f and multiplied by the Jacobian of this change of variables. Again, kind of thinking of this as a row vector of partial derivatives. This is another row vector, and this is a matrix now of partial derivatives, because phi is a function from a vector to a vector in general. Sorry, that's a horrible phi. Okay, something like that. Okay, so now we'd like to upper bound this thing. We want to get our upper bound back in terms of the gradient here. So the natural thing to do is to slap some norms. This is just the norm of a vector, so the usual 2 norm for a vector. Slap it on both sides. That's perfectly valid. And then use the fact that if we think about how are we going to bound the product of a matrix and a vector, we kind of think about the operator norm of a matrix, right? So if you just have a generic matrix A, and you want to look at a product with some generic vector x, let's say, then sometimes it's called the induced norm of the matrix. This is going to be smaller than what you denote as a operator norm or induced norm, 2 norm. There are lots of different terms for it, multiplied by that norm of the vector itself. Maybe you've seen an alternative definition where instead you write down that the operator norm is equal to the what do you want to do? Supremize over all. You can write it like this: ax divided by x, the norm of x. So you're trying to say, what's the worst I can do? If I can pick any vector x, how big can I make this product ax? And how big you can make that product is related to this operator norm here. Okay, so almost done with this. So let's skip down to here, and now we can look at this. We can look at the norm of this matrix product and just use our definition of the operator norm, and we can see that this will be upper bounded by the operator norm of our change of variables. Remember, this is a matrix. Put the operator norm there, multiplied by the just the usual vector 2 norm of our gradient. And then we're pretty much done. This is a little bit nasty to have this thing floating around as a function of nu. We would really like to have a constant back here in our upper bound. So the last thing that we need to do is find some kind of upper bound, or assume some kind of upper bound for this as well. So let's just suppose that the biggest that this could possibly be, we'll just make the assumption that this thing here is always going to be smaller than some value. What did I use? P. Let's just say it's upper bounded by p. So now we can go back over to here, and we can kind of wrap things up. We look at the left-hand side of this guy, and we've got f of theta minus f star. That's our suboptimality gap that we wanted, is less than or equal to 1 over 2m. That was just coming from our strong convexity of our reformulation. And then we can plug in this upper bound that we have we can plug in this upper bound that we have for the gradient. Although we should, if we want to plug it in, let's now go through retroactively and just square everything. Everything will still hold. So we put the p from our upper bound here, and we have our gradient norm squared. Okay, and that's our PL inequality. It has a slightly funkier constant here because there's a few extra terms going on, but you can see that the suboptimality gap is in fact upper bounded by the norm of the gradient, and it's back for the original function f that we cared about, not our strongly convex function. Okay, so not too far behind. Let me go through the summary of that quickly, and then, but if there are questions now, by all means, jump in. So what we showed is that as long as f actually had this finite minimum, if f does not have a finite minimum, you're kind of in trouble. There's nothing you can do to lower down the suboptimality gap. It's going to be infinite. And it has this m strongly convex reformulation. Remember, that means that when I plug in my change of variables, this function that I get is h is not only convex, but strongly convex. So as long as, if this holds, then this function f also satisfies this gradient dominance condition called the PL inequality with this special constant. And here, in order to make this a constant, we had to assume that we had some upper bound on the operator norm squared. Oh yeah, I probably should have squared one of those, but let's just say it's squared. We had to upper bound the operator norm, or assume that upper bound exists. So it's worth pointing out that the quality of this bound depends a lot on the conditioning of this function phi. In particular, if this Jacobian squared gets very big, so p gets very big, then this constant is going to become very large as well. And if you have a large constant here, it kind of makes the bound vacuous, because if this constant is huge, then the gradient could get very, very small, but the upper bound that you have on your suboptimality is still huge. So we want this constant to be as small as possible. So we have to worry a little bit in practice and in analysis a little bit about the conditioning of our change of variables. Okay, and yeah, I think there was a great question earlier, but we won't prove it today, but LQR actually not only has a convex reformulation, which we're about to see, but a little bit briefer than I would like, we're about to see, but it actually has a strongly convex formulation as well. So this analysis more or less goes through for LQR, and you can conclude that LQR does satisfy this nice gradient dominance property. Okay, I'm going to just completely skip convergence rates at the moment, just for time. Okay, yeah, let me pause there. Are there any questions at all on that? It was kind of technical, but hopefully the main idea kind of came across, that we did find a quantitative relationship between these convex reformulations and this gradient dominance condition that was in turn our quantitative notion of what it means to have benign non-convexity in the function. Yeah. Okay, so yeah, we've got about 20 minutes, so it might be a little on the brief side, but we're going to conclude by looking at these convex reformulations for LQR in particular. So at the moment, we've just been talking very kind of abstractly about this change of variables given by this function phi, but we haven't, except for the silly arctan squared example, we haven't really seen what these look like. So now I'm going to take some time. I feel like I owe it to you to show you what they look like for a real control problem. Okay, so let's just recap LQR briefly. Hopefully, has Russ covered LQR so far? Okay, great. So we can be fairly brief with this. It's obviously the linear quadratic regulator. Why linear? That comes from the dynamics, which are linear in the state and the action. In today, or for right now, I'll consider the version where the initial condition is random, so it's going to be normally distributed with zero mean and some variance w. That's not super important, but just to say that everything is deterministic except for the initial condition in this case. Quadratic for the quadratic cost, which we've seen before, quadratic penalty on the state and on the action. And the policy, which happens to be optimal in this setting, is just a simple static state feedback gain. Okay, great. And the specific problem that we'll consider is the infinite horizon. So I sample my initial condition from this normal distribution, and then I want to look at the total cost that I accumulate over all time, over infinite time. So hopefully the system is going to decay down to 0 so that this integral converges. And we look at the expected cost. So for any given trajectory, it's going to depend on the initial condition that we happen to sample. So what we want to minimize is what's the expected, what's the average cost over sampled initial conditions. Okay, so the first thing we need to do is compute the LQR cost, see what it looks like as a function of the policy a little bit more specifically. After all, we're doing kind of policy search here. The main property that we need to put the LQR cost into a little bit more convenient form is this so-called cyclic trace property. So this is just, you've probably seen it, it's just a nice property from linear algebra that whenever you have two matrices for which this is actually compatible, the transpose is not important, I don't know why, you don't need that at all. You can essentially rotate the matrix around so that you can do this kind of cycle. You can move the M transpose over to the other side, and will preserve the trace of this matrix product. It's just a simple property from linear algebra. So if we look at the quadratic cost, we can start to use this property to put it into a slightly more convenient form. So if we start with this term here, x transpose qx, we notice that this is just a scalar, right? So we're thinking of this as like a row vector because of the transpose, a matrix, and a column vector, so it's just a scalar. So we can put the trace around a scalar, and that changes nothing. Trace of a scalar is just that scalar back. And then we can use our cyclic trace property, and we can cycle this around here. So you see that I brought that x transpose over to the other side there. Not clear why this is useful so far, but it will become clear in a second. We can do the same thing for our costs on the control input. What we do is we replace the u with the feedback policy. So we plug in the kx here, same thing here, but with the transpose. And then we do the same trick. We apply the cyclic trace and move this over to the other side to get this thing here. Okay, so yeah, again, not really clear what's the point in doing this. It makes it a little bit nicer to write down the cost. So if we plug in the same kind of idea here, again, we're going to have the trace, I'll just abbreviate to TR, of Q x transpose. I'll just drop the time dependency just to be clear. Same thing here. We have the trace K transpose RK x transpose. Again, just copying directly from here. And what we can see appearing is this term starting to show up, which we can think about factoring out. This is showing up linearly. Everything is linear. It's linear in this term. The whole thing is linear in the integral. So what we can think about doing is really writing it like this. Have our let's take the trace. Let's take Q. Let's move the integral in, and then let's have our xt dt. Hopefully that's clear. These are supposed to be functions of time, but in the interest of time, I delete the time here. Here we also have trace of k transpose rk, and again, just going to move that integral inside. So have the xx transpose dt as well. Okay, so as I kind of alluded to, we have this integral. These integrals should obviously be from 0 to infinity as well. So we have this integral of x transpose showing up. I have dropped the expectation in the previous line just because it wasn't necessary for the algebra. Oops, shouldn't have done that. Anyway, but it is, we should have the expectation in there to compute the expected value of the cost. So we can define this matrix x, and with x defined as follows, we can really write the cost. Let me write it like this. The loss function of some policy k is going to be the trace of q x, this is exactly coming from here, plus the trace of k transpose r k x. So just making that substitution. I'm going for time. Not so bad. Okay, so so here is our cost function that we just derived. I just lumped these together in this particular equation. And we can see that it obviously depends on k. which shows up here, but it also depends on this x. This x we defined, but it also happens to satisfy this Lyapunov equation. So if you wanted to compute x, you don't actually have to solve this integral. You can just solve this Lyapunov equation. Now, we do have a proof of that, but there's, we're not going to get to that today, but, and it's not very insightful proof anyway. So hopefully you can just kind of take my word for it today that it will satisfy this Lyapunov equation. Okay, so now what was the point of all that? After all that kind of algebra, we can now kind of quite clearly see why LQR was non-convex in the first place, and also how we can come up with a convex reformulation of it. So first of all, why is it non-convex? Let me just literally write down the optimization problem of minimizing this cost function subject to this constraint. So I've just rewritten that here. But I've highlighted the decision variables. These are the variables we need to pick in blue. That's the gain matrix K, as well as this matrix X here. And you see that the problem, the issue, the reason why this is a non-convex problem is that we have these bilinearities. We have this product of K and X appearing everywhere. Here it's quite clear. It's showing up in the constraint, and it's also showing up here in the cost as well. It's even worse because there's an extra K over here, so, but it's at least bilinear. So this is a major source of non-convexity. You can see this for even for a scalar example. If we take these particular values and we just plug it in to our Lyapunov equation, we get something like, let's write it out, -1 plus K times X, exactly the same thing. So there's going to be a 2 there, plus 2 is equal to 0. So if we rewrite that, we can see that X is going to need to be -1 over K minus 1, I think. So just cancel those two, divide by 2, take it over the other side. We should get something like this. Sorry, going a bit quickly now for time. And then if we were to plot this function as a function, we plot x as a function of k here. See k and x. We see that this thing is going to blow up at 1, I suppose. So it's going to be asymptotic. When k is equal to 0, oh, yep, it should be 1, I guess. And then when k gets very big negative, the denominator is going to dominate. So it should look, I don't know, something like this, right? This is clearly a nonlinear function, is all I'm really trying to say, is that there's this nonlinear relationship between x and k. So this is a nonlinear constraint. And if you pass that nonlinear relationship back into here, it's going to kind of get messy. So again, we have this nonlinearity, non-convexity showing up. And now let's see how we can get rid of it. Okay, so the problem was the bilinearity. So the simple solution is just to get rid of the bilinearity with a change of variables. So anywhere where we see a kx, we just replace it with a new variable y. So for instance, we can rewrite our Lyapunov equation here in terms of our new variables. So we can take ax, that's coming from here and here. And then instead of plus bkx, we now just have plus by. We can do the same thing over here, xa transpose, don't forget the transpose up there. And then instead of, what would it be, xk transpose, we just have y transpose times b transpose plus w. And that's going to be equal to 0. Now this is, in all of our decision variables, I probably should have used a different color, but in all of the decision variables x and y, this is now a nice linear constraint. How are we doing for time? 10 minutes, not so bad. Yeah, I will skip the cost. For the cost, we have the same thing. We can also make that change of variables. It's going to turn out it's not going to look it's not going to be linear, so it's not going to look very convex, but it can actually be made convex. So yeah, let me kind of definitely skip that proof. So if we make that change of variables, we're going to get something like this. Obviously, it doesn't look very convex with this x inverse showing up, but it turns out with something called the Scherr complement, which I'm very happy to talk about offline, we can reformulate this in a way that even though it is already convex, we can put it into a form that is linear, which is what these semi-definite programming solvers like to pass. They need to have a linear formulation to input to them. So yeah, I will, in the interest of time, kind of gloss over exactly how you will do that reformulation. But the main idea is to introduce a slack variable z to upper bound this term, which is convex, and then replace this kind of nasty nonlinearity with this nice linear matrix inequality. So yeah, I apologize that I didn't quite get to see exactly how that goes through and why that remains convex. But the key point is that once you've made these changes of variables, you end up with the following optimization problem. And you can see that it has these 3 decision variables: the slack variable, the original x, as well as the new y that came from our change of variables. The objective is linear in our decision variables. Our Lyapunov equation, like before, is also linear in the decision variables. And we also have this linear matrix inequality. So this is a nice convex semi-definite program that we can solve. And of course, once we've solved it, we need to get back the policy. And to do so, we just look at our constraint that we had. So we said essentially that we had this change of variables, y is equal to kx. And we just hit both, oops, y is equal to kx. Get ahead of myself. We hit both sides with an x inverse to recover our optimal policy k. Okay, and so you could solve this semi-definite program as an alternative to solving, say, the Riccardi equation, which is probably how Russ showed you the solution of LQR before. Okay, so yeah, in the remaining time, let me just say that this is with this change of variables, you can solve LQR as a semi-definite program. But to do so, you would need to have the model. It comes back to the question that we had before, like, should you solve LQR just as gradient descent on the policy parameters k, or should you solve the convex version? I would say that if you have the model, so you see how you need to know A, B, and W, and Q, and R. So as long as you have the full model, you can write down this program, and you can solve it. But if you don't have the model, then the only thing you need to know to conclude that gradient descent in the space of the policy parameters k will converge is that this reformulation exists. So I just want to emphasize, you don't need to ever use this reformulation to run gradient descent. You still just run gradient descent on the loss function in terms of k. You just need to know that this reformulation exists out there. Okay, so yeah, 5 minutes to go. Let's yeah, let me leave it at that for now. There's some slight subtleties in exactly what the kind of phi, what this change of variables looks like, but yeah, I'll put the slides online and hopefully it's kind of self-explanatory. So the last thing that we'll talk about before we wrap up very quickly is we'll go back to this output feedback problem. And so we saw kind of at the beginning, we had 2 very similar problems. They both had linear dynamics. They both had quadratic cost function. Not only that, but the same linear dynamics and the same quadratic cost. But one had partial observation and resulted in this kind of pathological non-convexity. The other one was LQR with the full state feedback and resulted in this nice benign non-convexity. So the difference between them was that for LQR, as we've seen, we have this convex reformulation, whereas for this problem with partial observation, there's no known convex reformulation for the static feedback case. That's partial, that's output feedback, you would say, but with a static gain. So do we, Alex, how much time? Do we actually have 4 minutes, or do we need to let people go? Okay, great. So let me just show very quickly what does go wrong in this output feedback case. First, what goes right in the state feedback case. Remember that we had these bilinearities. They were problematic. So we introduced this new change of variables, y, to get rid of the bilinearities. And then we really had this kind of relationship that we needed to respect, but we just dropped the constraint. We never enforced that constraint. Why didn't we need to enforce it? Because for any y and x that we found, we could always recover an x. We could always recover a k that satisfies this constraint. In other words, this constraint is saying that we need to find a y that is in the row space of this matrix X. And because X was positive definite and full rank, the row space, Y is always going to be in the row space of X. In other words, this constraint is trivially satisfied. In the partial observation case, now instead of having this k and x, instead of the state going directly into the policy, we have this matrix here, C. Remember, now we have to do, y is equal to c of x, and u is equal to k of y instead. So we have this kind of annoying C showing up. We could try the same trick, try the same change of variables to get rid of this bilinearity. Except the problem is now what this constraint is saying is that the y that we search over has to be in the row space of this matrix, C of x. And in general, this matrix C is you used to say short and fat, but you can't say that anymore. So this is like a vertically challenged and wide matrix. So it doesn't span, its rows don't span the whole space Rn. So in general, if you recover a y, if you find a y and an x, you're not going to be able to satisfy this constraint trivially. It's probably not going to be the case that y just magically lands in the row space of this matrix, so we can't satisfy the constraint. So with that, a little bit rushed on LQR at the end there, but that will probably do it. If they've got a little bit of time for questions, of course, so happy to take any questions. Yeah?
Maybe a bit abstract. The idea for this direct policy search is as long as we have a loss function and the data to sort of formulate that loss function for the system, and it does not have pathological non-convexities, it should succeed, assuming that immense computational power and all that.
Yeah, exactly. As long as, there's a couple of subtleties. So in any given problem, you might want to worry a bit more about the convergence rate. So we talked about what happens if this change of variables is not very well conditioned. Maybe that constant becomes really bad. So that's a concern. As you mentioned, you might still need a lot of computational power to even run the kind of gradient descent. That's another really good point. But yeah, you're right. If you're kind of dealing with this benign non-convexity, you can be more confident that local search is not going to get stuck.
So I'm just curious, like, so the way that LQR was derived in this class was through the algebraic Riccati equation.
Yep.
So, like, is it just difficult to say anything about the convexity of that formulation? Is that why you have to rewrite it in the STP way? Is that why, why can't we make some statements about convexity using
Yeah. No, that's a really good point. Let me repeat the question. We saw that we can also solve LQR via the algebraic Riccati equation. Why can't we somehow go from the algebraic Riccati equation directly to analysis of policy search? It's a very good question. Maybe you can. I will say that there is a nice relationship between this reformulation that I presented today and the algebraic Riccati equation. So today it really looked like a trick, like, oh, we had this bilinearity, so we just introduced a change of variables to get rid of it. But there is a much more principled way of arriving at that change of variables, and that has quite deep connections to the algebraic Riccati equation, as well as dual dynamic programming. I'm not sure if Russ has talked about this idea of the Bellman inequality. Okay, Alex is shaking his head. Anyway, maybe later. It has deep connections to other ideas in dynamic programming. So I'd be happy to talk about it offline. But yeah, there was one other question. No, okay, great. Yeah, great. Well, thanks very much.